Hello, welcome back to Compressible Flow. I'm Professor Steve Miller. Today we'll be talking about the induced velocities behind the shocks. In the previous class we looked at the induced velocity itself. We'll return to this and look at particular physics and extend the theory a little bit more. Then we'll change subjects and look at the so-called reflected shock waves. That is when a shock wave reflects off a surface. It could be a moving shock wave, and later in the class we'll extend this to standing shock waves that are impinging on walls. We'll look at these particular cases where the shock moves and bounces, that is, reflects off the wall in the opposite direction, and try and understand what happens, of course, to the thermodynamic quantities after the shock. Then finally, we'll have a third major subject of this class, which is the Rayleigh-Pitot formula. This is an important formula where we'll use to try and discover the properties of the flow in front of the probe in a supersonic flow. And you'll see from our previous analysis that we assumed isentropic flow. Here we relax those assumptions and attempt to find the problem with shock waves around the particular probe. So you can see it has very much and good practical value. Let's begin. Usually in class, I like to show a particular video where we show the induced velocity behind shocks. In the previous class, we developed a formula for U sub p, the velocity behind the particular moving shock wave. That velocity becomes very large, as you see in this one particular picture from a movie. This in particular is figure 152, which I've written, induced velocity behind a nuclear explosion blast wave, which caused the trees to bend and break. And you can see movies like these online, and I'll try and show one particular movie in class. So you can see these particular trees are being bent to the right. So obviously, the blast wave or wave from, say, some sort of explosion moved from left to right and caused the induced velocity to move in the right direction. Let's return to our subject of moving normal shock waves. You'll see that indeed a velocity is induced by the shock wave, as we derived, and must happen due to continuity, and it must occur in the direction of the wave. This induced velocity can become very, very large, but we might wonder and think, how large can it be? What is a range? Perhaps there's an asymptotic analysis we might perform to understand this. It is always in the direction of the particular wave front, as we derived in the previous class. But you might imagine there's particular shock systems where perhaps the velocity might be changed in terms of its induced directions. Right now, we'll just focus on normal shocks. We might also want to know what is the induced Mach number, and you can imagine we'll try and take U sub p and divide it by C sub 2, the Mach number in the direction of the wave after the wave front. So let's first seek the last point. What is m sub p behind the wave, behind a moving normal shock wave? In this case, we can write in equation 427 of this particular slide deck, m sub p, and it'll go as U sub p, the velocity of the fluid behind the wave in the direction of the wave, divided by C sub 2. Now here, C sub 2 is the speed of sound behind the shock wave. If we define a perfect gas, and assume it's perfect, then we can say C sub 2 equals the square root of gamma r t sub 2. But we won't try that yet. What we'll do is take ratios, and we can write the second term of 427 as a third as UP over C2 times C1 over C1, and rearrange those two particular fractions in the third term, and write UP over C1 times C1 over C2. We then can replace the definition of square root of gamma RT with T1 and T2 respectively, and put it in the numerator and denominator respectively on the right-hand side of 427. We'll then have the first term, UP over C1, times the square root of T1 over T2. You can see the factors gamma and r are constant, and we cross them out inside the argument of the square root operator. We then take T2 over T1, which we previously found as the static temperature ratio across the moving shock, and our full equation for U sub p, which we derived in our previous class, and insert it into the right-hand side of 427. And therefore, we find a closed form formula only as a function of P2 and P1 for, of course, the Mach number behind the induced shock. You can see that it's only a function of P2 over P1, which is the static pressure rise ratio across the moving shock, and gamma, which is a constant due to our previous assumptions. Now you might say, with this particular formula, what is the absolute maximum Mach number that could be induced by a moving shock wave? That is what is physically possible given the assumptions we've made. Well, in this case, the shock wave will move faster and faster, of course, with a higher and higher pressure ratio and vice versa. And you can see that through the equations by graphing them of W versus P2 over P1. Therefore, if we let P2 over P1 become very, very large, then of course we'll see what happens to a higher and higher Mach number shock. In this case, we'll take the limit of P2 over P1 of equation 428, the bottom of 504, and we'll find, if you do the limit correctly, 2 over gamma times gamma minus 1 all over to the half power. Excuse me, all to the half power. You'll see indeed that if we put in gamma 1.4 for air, which is, I guess, our favorite value of gamma in this class, then we'll see that the limit indeed goes up to 1.89. That's the Mach number after the moving shock wave can go up to 1.89. This is amazing because it shows indeed with a very powerful wave, a moving shock wave in this case, the Mach number behind the wave in the direction of the wave must be 1.89, defined as UP over C2. So we can indeed have supersonic flow induced by a moving shock wave, which of course has applications in particular exotic and theoretical propulsion systems being designed in aerospace engineering. It is very unlikely, though, that m sub p would be greater than 1 in practice, and you would have to have very strong shock waves, which are not typically induced in nature, and very, very rarely induced in, of course, man-made type devices, like in engineering. Let's now look at the moving shock wave case again and review important concepts, but we have not looked at, of course, how the stagnation or total values move across the shock. So we've looked at the induced Mach number. Now let's look at stagnation conditions of moving shock. We'll see that indeed H naught, that's the total enthalpy, is conserved. It's conserved in the standing normal shock wave. However, it is not conserved in the moving reference frame. This is because, of course, the velocities and the reference frame matter. The velocities relative to the reference frame. So we change the reference frame, we'll change our relative velocities. Now the velocity in front of the shock we defined as, of course, the velocity 0, and the velocity after the shock we defined as u sub p. So for a moving normal shocks, we might write h sub O2, that's the total enthalpy after the moving shock, will go as the static enthalpy after the shock plus u sub p squared over 2. This is a little bit different where in front of the shock, HO1 equals H1, because of course U1 is 0. So how do we find the total properties after the shock? We'll try out the energy equation. Here we can write rho of the material derivative of total enthalpy will go as dp dt. Where indeed does this equation come from? It's actually, of course, a form of the energy equation, written with pressures, with our assumptions of perfect gas. So here we see that the flow is indeed unsteady, because of course there's a moving normal shock wave, and as you recall, the solution is dependent on x and t. Therefore, we can see from this particular formula that since h naught is indeed changing from bullet point 2, that also indeed that the pressure must also be changing from the formula. And so dp dt is not equal to 0, and the material derivative of the total enthalpy is not equal to 0. Let's now summarize our moving and stationary shock relations. In figure 153, I show a summary table of the relations. The right column is the stationary normal shock relations. The left column is the moving normal shock relations. Let's look at stationary first. Here, there's a change of variables from this particular text. They say S over A1 is M1. That's the Mach number in front of the stationary normal shock. That's S over A1. So A1 is the speed of sound in front of the shock, and S, of course, is the velocity in front of the shock. They then have the normal isentropic relations in front of the shock, which we defined before, and then they have the closed form formulas for temperature, static temperature, Mach number after the shock, which goes as S minus V, and here, of course, V is the induced velocity behind the shock, and P2, PO2, and TO2 are the static and total pressure and temperature values respectively. You'll see the right-hand column is written entirely in terms of M1. They've also introduced, of course, V, the induced velocity after the shock. So you can see, if you look between the two columns for the same quantities, you can easily convert between moving normal shocks and standing normal shocks. The left column, of course, is moving normal shocks. Here's M1, the Mach number in front of the moving normal shock, and it has a velocity 0 divided by the speed of sound in front of the shock. It's 0. You can go down the list and see right away M2 is V over C2. That's the velocity induced behind the moving shock. Take a few minutes and look at these formulas, and I think it'll help you understand the physics of these particular moving shocks a little bit more clearly. Let's now turn our attention to the incident and reflected shocks. Here, an incident shock is the original shock, as we analyzed, it's moving, and the reflected shock is what we call the shock wave which has bounced off a wall. It's reflected. So the incident wave and reflected wave are the incoming wave and the reflected wave from some surface or some flow phenomena that's reflected the shock. So we'll turn our attention to this particular case. And we would like to know what happens when a shock wave hits a surface and bounces off. And a lot of different things can happen depending on the boundary condition. The acoustics boundary condition, which we talked briefly about earlier, is dP dN is 0, where n is the unit normal from the wall. P is the static pressure. You can see indeed this is a linear analysis. Unfortunately, it's not very much applicable. So the shock wave is indeed a non-linear phenomena. So we can't necessarily use the traditional infinitesimal acoustics boundary conditions. Let's look at visually what happens with the reflected shock wave. Here in figure 154, I've shown Schlieren images from a particular movie of a reflected shock. The time increases from the upper left to the lower left, and then the upper right to the lower right. So here is time approximately 0, or less than the start time, 36 microseconds, all the way to 1506 microseconds, then up to the right, a picture taken at 1786 microseconds, all the way down to 3676 microseconds. Now what you're seeing here in these particular pictures are Schlieren images. Remember, Schlieren images are density streaks taken in the flow with a high-speed camera. These two particular lines are simply put there for a frame of reference, and they're fixed at 21.3 centimeters apart. Originally, there's nothing taken. There's no shock wave. And then we take a picture at 36 microseconds, and we see this little line here, which is marked as the incident shock wave. We can look down and see that it's moved from right to left over a time interval of 316 microsecond minus 36 microsecond. And here's the shock wave. My cursor's moving. Then the shock wave goes off the screen, and a time goes by where it travels down the tube, we go up to the right, and then it reflects. It hits a wall, and it reflects somehow. Then we go down more time, and once again it enters a viewfinder. So to the left of these images, the extension of the shock tube with a closed end. And indeed, we see a reflected shock here, moving from left to right and increasing times, and of course then an exhaust back to the right of the tube. You can also see some more granulations in these photos as there's some turbulence to rise in the flow. You'll also see that the shock wave itself is a much, much darker line. Remember how dark and how light the image is signifies a range of density gradients from the Schlieren image. So you might imagine in these particular photos that indeed the intensity of that shock, that is the rise of pressure and rise of density gradients, has become larger and larger through its reflection. And so we've made a first physical observation. Then when a shock wave impinges on a wall at standard conditions with no impedance, then it will reflect as a stronger wave. Let's now try and analyze this particular problem. Here in figure 155 of the slide deck, I've shown a particular schematic of the incident moving normal shock wave before its particular impingement, which we show in the left side of figure 154. In this case, our shock wave is moving from left to right. In the images, it's moving from right to left. Let's start and always look at the reference frame where our shock is moving from left to right. You'll see in this particular case, we have a state 1 and a state 2, and we limit and label this as an incident shock. This is the wall of the shock tube, and here's the end wall on the right where the shock wave will bounce off. Initially, the gas is at rest in the tube, so we can write U1 equals 0. The velocity of the shock will be W, and the induced velocity behind the shock will be U sub P. So this is our initial problem. We have the shock wave coming down the tube. The shock wave then hits the wall and reflects. But now the shock wave reflects with a different velocity off the wall. We should not expect the shock wave to reflect at the same velocity like we would an infinitesimal wave like an acoustic wave. Indeed, this is a nonlinear problem, and we would expect a different shock reflection. In figure 156, I've shown this. Here, we'll call the speed of the reflected wave W sub r. That is, the r's for reflected. Then in region 5 of the flow, behind the reflected shock wave, after it bounces off the wall, we'll write U sub 5 equals 0. Why would the velocity behind the reflected wave be 0? The answer is simple, and it's due to continuity. That airflow has nowhere to go because the walls are solid. If the walls were porous in some cases, then of course U sub 5 may not be 0. Nonetheless, there will also be a velocity, U sub p, which was originally induced by the original incident wave. Now, the reflected wave velocity will be going into an incoming velocity, U sub p, and we'll have to make a, of course, substitution in our equations to account for U sub p of a non-zero U sub 1r, that is the velocity before the reflected shock wave. Let's try that out momentarily. Some additional notes and observations from this problem. As I mentioned, U equals 0 to the right of reflected shock, and I've already noted that's due to the conservation of mass. You can write a control volume over the particular case in region 5 and prove this to yourself. WR is the velocity of the reflected shock opposed to W. So W is the speed of the incident shock, and WR, of course, is going to be in the opposite direction from a normal shock impedance. Later in the class, we'll look at oblique shock impedance, and things will change a bit. However, the same ideas will hold true. Now, the strength of the reflected shock will definitely be dependent on U sub r equals 0. That is the velocity of the reflected induced velocity. So U sub r could be seen as U sub 5 in this case. That's because related to the induced velocity, we find the related reflected shocks. So we can understand the physics of this particular problem by considering the wave motion of a graph of t versus x. I think you can see where I'm going with this now. Let's look at one particular figure in 157, which I've labeled the space-time of the reflected normal shock wave. Let's analyze this figure relative to the graphs. On the x-axis, we have the x coordinates, of course, x1 and x2, and they would be, of course, from left to right in figure 155. The y-axis is time, and so we're plotting the spatial position of the wave front as it propagates from left to right and then reflects off the wall from right to left. So initially, our shock wave is moving towards the wall, the incident shock, and it's at position, say, x1 and time 1. At a time t2 later, delta t2 later, t1 to t2, we're at position 2, x2. So now the shock wave hits the wall. And you know this is the wall because, of course, the wave changes direction rather abruptly. The wave then moves to the left, and it's, of course, labeled the reflected shock wave with velocity WR, and it goes to 0.3. Look at the particular slopes of x1 over t1, and of course, maybe somewhere position x3 with x2 between time 2 and t3. You'll see indeed that they have different slopes, and we'll see indeed from our analysis that the velocity of the reflected shock is very much different than the velocity of the incident shock. Now, let's try and trace the position of a fluid particle that's massless, or more ideally, a fluid parcel, which is a differential element of the fluid. Here at x1 times 0, the fluid is stationary, as we see as the velocity of the flow before the incident shock. The incident shock hits that fluid parcel, and then it has an induced velocity, and it pushes that fluid after the incident shock towards the wall. And that's drawn by this particular line. And you can estimate velocities, of course, by the changes in x and t. The velocity is then going towards the wall, and then the reflected shock occurs and it impinges on that fluid parcel, and the fluid parcel goes to the shock wave, and its new induced velocity is 0, which must be true due to continuity. And you can flip back and forth between these three pages, and look and try and understand what happens to the fluid parcel and the position of the shock wave between incident and reflected waves throughout the continuum of the fluid, with one discontinuity being the shock wave. Let's look at those quickly. 155, 156, 157 figures. Let's once again look at and make some notes about these particular diagram which I've shown. I've noted that the dashed line is a particle of fluid parcel path. The slopes of this particular path is 1 over W and 1 over WR, where W is the shock velocity and reflected shock velocity respectively. You'll also notice that we observe in experiments and predictions which we'll be making, the magnitude of the reflected shock wave is always less than the magnitude of the incident wave, which we've tried and drawn in this photo accurately by looking at the slopes with x and t for velocity. You'll then also see that the reflected shock wave velocity and the induced velocity from the incident shock of the gas is relative to the wave. Therefore, WR is the velocity of the gas behind the shock wave relative to the wave. Take a few minutes and consider these factual statements. Let's now try and analyze our reflected shock problem. Here we'll use the same set of equations we used previously, but we'll be substituting in these particular definitions for the left and right hand side. Here we have the state of the gas before and after the reflected shock wave respectively. So the continuity equation that I've written in 431, you'll see indeed it's the density before the reflected shock times the velocity in front of the reflected shock, which will be written as WR plus UP. WR is the speed of the reflected wave in the left direction, plus the induced velocity from the incident wave in the right direction. The right-hand side, of course, will be the density after the reflected shock wave times WR itself, which is indeed the velocity of the reflected shock wave. Now let's look at the momentum equation. We'll write, and it's the simple substitution of P1 plus P rho 2 times WR plus UP squared equals P2 plus rho 2 WR squared. So once again, we've taken our momentum equation in one dimension and substitute in our relative velocities. We've done the same thing for energy equation written for H with kinetic velocities. Static enthalpy plus the velocities over 2 squared equals H2 plus WR squared over 2. So try to make those substitutions yourself. It's exactly the same as we've done in the past two derivations. We can then also derive and define the incident shock wave Mach number, which we'll define as W over C1, where of course C1 is the speed of sound in front of the reflected shock. But we'll have to substitute C1 to be the appropriate value of the speed of sound. We'll call that C sub R, the speed of sound in front of the reflected shock, which is of course nothing but the speed of sound after the incident moving shock wave towards the wall. The numerator will once again be the speed of the shock wave. It's the reflected shock wave speed plus the induced velocity. Now, unfortunately, these equations do not have analytical solutions, and so you must have to use numerical approaches. We have these equations and we have to do numerics. That is, we cannot find a closed form analytical solution. To try and proceed, we'll assume, to make some assumptions in progress at least, that the fluid indeed is a calically perfect gas. We'll use the exact same solution approach that we previously developed. And going through that approach for the moving shock wave, which we developed, but using this set of equations, and except the velocity form's different, we can find the exact same type of equations, but with substituted values for velocity. Here we'll have an equation for the reflected Mach number as only a function of m sub s, which of course is the Mach number of the incident shock properties. So the Mach number of the incident shock will be a function of m sub r. The Mach number of the reflected shock is the same thing, of course. But you can see you cannot create a closed form solution of 436. You can't solve for mr explicitly. And so we would need a numerical method to do this. Now, We can also look at the other equations we developed. You can look for, say, the change of pressure across the reflected shock, and that'll be only a function of the change of pressure in front of the incident shock. So we would follow the exact same solution approach for that equation too. So here, delta P, the change of pressure, the pressure rise across the reflected shock is exactly a function, it's not equal, of the change of static pressure of the incident shock. So take a second to see this equation, and the solution approach is exactly the same as this traditional approach we showed previously. So I'm not going to waste your time rederiving it. Let's look at the results of the particular delta P of the reflected shock with respect to the incident shock. And we'll look at the magnitude of those pressures from the delta P. This is indeed written as a function of the Mach number of the original incident shock. So the Mach number is on the x-axis, and the rise of pressure at, say, m equals 1 will be 0, and the rise of pressure from the reflected shock will be, of course, be 0 because there's no shock. Now, as we increase the Mach number of the original incident shock, that is, it's W over U1 in this case, let's say up to 4, and you'll get a delta P, an overpressure of 20. So from the first shock wave, we would feel 20 atmospheres. Now, when the reflected shock returns, we will have another overpressure from delta P, which will be much higher. And you can see that's at about 110 atmospheres. So if a shock wave moves towards a wall, the total pressure rise after the reflection has occurred will be about 110 atmospheres. This is, of course, for gamma 1.4 at a standard condition T1 at 293 Kelvin. So you can see it's very easy to raise pressures through shock wave motion. And indeed, these concepts are used in particular aerospace propulsion devices like wave rotors. Let's summarize our derivation of the reflected shock waves. Indeed, the reflected shock wave problem can easily be solved by solving the moving shock wave problem twice, which is what we usually do in practice. Solve the first moving shock wave problem with our traditional approach we developed, and then solve it again with the new induced velocities, with, of course, a reference frame change to account for U sub P induced in front of the incident shock wave. Remember, the boundary conditions of the reflect shock wave are driven by conservation of mass. If you had, of course, some kind of different boundary condition where the shock wave impinges on the wall, you would have to account for that, and it may not have an induced velocity behind the reflected shock, depending on the boundary conditions. The properties will continue to rise after each shock reflection. For example, if we had a closed tube where the shock moves left and right and bounces back and forth multiple times, we might have, indeed, higher and higher pressures. Now, it's not necessary to remember any particular formulas for reflected shocks. Just use the traditional moving shock formulas and put in a substitution for the relative velocities according to the boundary conditions of the problem, and then I think you'll have great success solving these types of problems. Good luck with this. It's very interesting. Let's now turn our attention away from the classical moving shock problems and look at one particular measurement device. In your previous academic career, you've looked at incompressible flow to look at, say, pitot tubes and pitot-static tubes. In this class, we introduced the compressible pitot-static formula for isentropic flow and subsonic flows. But what happens when the flow Mach number is greater than 1? Of course, shock waves will form around the probe as the probe induces and disturbs the flow. We have to account for these particular shock waves. So we'll try and look at this particular theory and practice the pitot-static tubes that are placed in supersonic flow. You'll see that, of course, we will violate our assumptions of isentropy in this case, and we must develop specific theories to overcome these problems. Now, to do this, we'll have to look at our previous equations, but remember they do not apply to normal shock wave and will form if a probe is placed in a flow in Mach 1. I'll show pictures of this later in this class. We will need to account for this formation of the normal shock in front of the probe. So you can imagine the flow comes in and it impinges on the front of the pitot total pressure port. Indeed, that stagnation causes a standing normal shock wave in front of the probe. The shock wave creates a huge amount of increase in entropy, as we derived in this class. Therefore, we must account for this entropy loss to accurately measure the speed of the flow in front of the probe without a shock wave. We have not yet looked at the history of Rayleigh-Pitot. Let's take a few seconds to do that now. Rayleigh-Pitot, of course, was a Frenchman, and he was born in 1695 and lived through 1771, which was a pretty healthy life for that time period. Indeed, he was a hydraulic engineer, and he was the inventor of the Pitot tube, which, of course, we name after him today. He was asked to measure the flow speed in a river in France, and he went out and, of course, did this, and he developed this instrument to do it. He built aqueducts at Des Saint-Clément near Montpellier, and the extension of Point du Gard in Nimes. He was a member of the French Academy of Sciences, and in 1740 a fellow of the Royal Society of course, England. Here's one particular picture of Rayleigh-Pitot on the right, and note that the T is silent because, of course, it's a French name. And it very much reminds me of a contemporary selfie. You can see that in these types of photos, he, of course, has his best outfit on. But in these types of photos, they lay out particular things to show that he is, in fact, a man of science with a book open to a particular page, just so subject, and a number of other instruments. This was very common for many people to have self-portraits painted in this way so that they could, of course, identify and show their status in society. Let's look at one particular Pitot probe experiment which I was involved in as a graduate student. And I'll try and show this video in class. Let's see what we're looking at here in the particular still. I've written in the caption that this is a 4-probe Pitot probe within supersonic flow, and note that there's shocks in front of the probes. And this experiment was conducted by one of my advisors, Professor Dennis McLaughlin of Penn State, and his grad student, Jeremy Velton. I was on the theoretical and numerical team. This is a jet flow, and so here's the nozzle, and this is a Schlieren image, by the way, so these are contours of density gradient, essentially. And the flow moves from left to right, and this is the exhaust of the jet. And what you're seeing here are these like little lines that look like diamonds. We call this the shock cell structure. They're shock cells which are contained in the supersonic flow, and we'll talk more about these in this class. We wanted to measure the particular velocities and Mach numbers in this particular flow. And so we developed a probe which we pushed into the jet flow, and it has 1, 2, 3, 4, 5 particular ports. So the flow moves from left to right, and you can see that these are stagnation pressure ports, and along the device there might be static pressure ports. Nonetheless, you can see in this particular Schlieren that there's a very dark line which forms in front of the probes. We put 5 probes in instead of 1, and that's a normal shock wave. Now, if this probe was not here in the flow, that normal shock wave, of course, would not be there. The normal shock wave is there only because we put the probe in the flow. So we must account for that normal shock wave in our theory because we've disturbed the flow of our measurement. Here's one particular picture of a total pressure Pitot tube placed in a supersonic flow. So once again, this line here represents a cross-section of a tube which is bent towards the flow, and the flow moves from left to right. Now the flow is supersonic, so unlike previous diagrams, a shock wave forms in front of the tube, and that shock wave has a normal shock right in front of the probe port. So the flow moves from left to right supersonically, it goes through the normal shock wave, and it comes in and stagnates at the entrance of the port, and we measure the total pressure. Now remember, we've shown in this class that there's a total pressure loss across standing normal shock waves. So the total pressure in front of the shock wave is higher than the total pressure we're measuring with the probe. But we need total pressure to, of course, estimate the velocity and Mach number of the flow. This is a very big conundrum, and this is where the so-called Rayleigh-Pitot formula came into being. Also in this photo, you see this dark checkerboard line and a light line. This represents where the sonic conditions are. Indeed, this part of the flow is supersonic, which is darker color, and the white color here, which is uncheckered, is the subsonic flow. So you know the flow behind a standing normal shock is subsonic. This also alludes to the fact that flow could be supersonic behind waves with curvature, that is, they're not incident with the flow direction. Let's try and analyze this problem in a few minutes. To do that, we'll zoom in at the probe face. This is a particular diagram in my figure caption which I wrote, is the diagram of the probe inserted in the flow. So this is just zoomed in at the probe face right in this area in front of the shock. So the shock wave curvature is basically normal to the flow. in front of the probe, and we have a supersonic flow in front of the shock wave by definition, and a subsonic flow after the normal shock wave. It's standing in front of the probe. And we go from state 1 to 2. We can use isentropic theory to go from the free stream Mach number to some Mach number in front of the shock, to state 2, a Mach number 2, which is after the shock, and then use isentropic theory to deaccelerate the flow to the stagnation condition, where inside the tube, of course, the Mach number is 0. So this is your typical diagram of the probe inserted into the supersonic flow. Let's try and analyze this problem in a second. Another way to set up the tubes is to put in the stagnation pitot tube into the flow and link it through the wall of a wind tunnel or aircraft vehicle surface, and have a second static pressure port upstream of the shock. And this way we can try and estimate what the static pressures are in front of the shock. We'll need to know some kind of thermodynamic information before the shock wave to try and solve these problems, which is a rather difficult thing to know and do in advance. So here we've drawn the shock wave, which is wrapped around the tube, put in supersonic flow, and we're measuring the total pressure after the normal shock, and we're able to get some kind of static pressure or some other information in front of the shock. That might be, for example, the ambient Mach pressure, for example, the atmospheric pressure. And so we'll get two quantities. We'll get one, like P1 or P sub infinity. That's the static pressure in front of the shock of the undisturbed fluid, say right here, where my cursor is, right before the shock. And we'll get P sub O2, the total pressure at the probe. Why did we write O2? The O, or naught, signifies it's the stagnation or total value, and the 2 denotes that it's after and state 2 of the shock wave. So there's isentropic flow from the shock wave surface after the shock to the probe face. So that stagnation pressure is constant between the probe face and the face of the shock wave, and in front of the wave and out in front of it in the flow, as long as there's no turbulence in the flow, of course. Here's another picture of an alternative diagram. Here indeed we have the same shock wave in front of a probe, but we've placed a pitot-static tube in the flow. Here the center hole is measuring the total pressure. It's like those maze diagrams as you were a kid, and we get a PO2. We also might get a static pressure. We might just call that P or P2 in this case. They labeled it P1, which is silly because of course it's the static pressure after the shock, and that won't have the same static pressure as the atmosphere. This is hollowed out and it goes up to the static pressure ports on the side of the tube. Remember, static pressure ports measure static pressure and total pressure ports measure stagnation pressure. That's pretty straightforward. So let's make some observations and then analyze our problem. First, we introduce the probe into the flow. The flow itself is undisturbed and no normal shock exists at that location where the probe is until we insert it. We put the probe into the flow, and of course then a normal shock is induced in front of the probe. If we're not moving the probe, the shock wave, which is normal in front of the probe to the flow, is standing, and therefore we can use traditional normal shock wave that's standing theory to analyze the problem. We would normally characterize the shock wave in normal shock wave theory by M1, but we seek to measure M1, and all our functions for normal shock waves are a function of M1. So we'll have to indeed seek a method to relate these particular measurements from the probe, PO2 and P, with the probe to find M1 and other properties in front of the shock as if the shock didn't exist. Remember, we want to know the flow properties as if the probe and shock did not exist. So please recall first the equation for stagnation pressure, static pressure, and Mach number across in isentropic theory. We have P naught over P goes as 1 plus gamma minus 1 over 2 m squared to the gamma over gamma minus 1. So now we have a total pressure, a static pressure, and a Mach number in isentropic flow. So we haven't accounted for the shock wave yet. Let's solve for Mach number. We can take 438 and solve, and 439 as m squared goes as 2 over gamma minus 1 times P naught over P, the total pressure divided by static pressure, to the gamma minus 1 over gamma minus 1. Now we can try and relate the dynamic pressure, that's 1/2 rho u squared, to some unknown quantities that we desire in the equation which we just produced. And this is something maybe we can try and measure. So we want to take this formula and convert it into something we can try and measure. That's our goal. So we can write 1/2 rho u squared and write that as gamma over 2 times u squared over gamma p over rho times p. So note that the p's cancel out and I've written gamma over gamma, and of course I've retained rho and moved it into diameter. So the first term and second term in 440 are exactly the same, but I've written as ratios P over P and gamma over gamma, and move gamma into the denominator, which is easy to do. So you see I have the same form. I can then rewrite that exactly as gamma over 2 times u squared over c squared times p. So you'll note in the denominator, I've changed this to the speed of sound because c squared goes as gamma p over rho as we derived in our first module. You'll see I've done this so I can write u squared over c squared as m squared. We then have gamma over 2 m squared times p, pressure. Look at this particular form of the equation with the previous, m squared. I can make in the substitution and simplify, and I get the right-hand side. And so I can write 1/2 rho u squared goes as gamma over gamma minus 1 times p naught over p to the gamma minus 1 over gamma minus 1 times p. You can check this mathematics for yourself. I encourage you to do it. Now I have a total pressure PO2 that's measured by the probe. I might write that as PO2 divided by P2 times P2 over P1 times P1. Here P2 over P1 is of course the pressure ratio across the standing normal shock wave. P1 is the atmospheric pressure. PO2 is the pressure measured by the probe, and static pressure is measured by the static port of the probe. Here P1 is the atmospheric pressure, and M1 now is the ambient Mach number. We can now rewrite our earlier equation for the stagnation static pressure ratio using normal shock relations as PO2 over P2 will go as 1 plus gamma minus 1 over 2 m squared to the gamma over gamma minus 1. Here in 442, using these relations through substitution, we can now, you see, I have PO2 over P2. Recall the corresponding static pressure ratio across a shock, which we earlier derived. P2 over P1 goes as 2 gamma over gamma plus 1 times m1 squared minus gamma minus 1 over gamma plus 1. So you see, in 441, I have terms PO2 over P2, which I've written in 442, and I have P2 over P1 to cross the shock, which I've used from traditional theory in 443. Let's substitute these equations in. Combining them, we have 444. It is the total pressure measured by the probe divided by the pressure in front of the shock wave, P1, the static ambient pressure in front of the shock. It's only a function of m1 squared. m1 is indeed what we're seeking to solve for. m1 is the Mach number in front of the shock wave induced by the probe. That is, the Mach number of the flow without the probe. We can simplify this further in 445, and I've boxed this equation because it's so important and it should appear on your formula sheets. This is the so-called and beautiful Rayleigh-Pitot formula, named after two people who we reviewed their historical context very briefly. Here in this formula, we have P1 in the denominator on the left. That is the static pressure in front of the shock wave. For external aerodynamic problems, that would be the ambient static pressure. M1 might be the ambient Mach number or the Mach number in front of the probe, or the Mach number with an undisturbed air without a probe at that particular measurement location. PO2 is the total pressure measured by the probe itself. And so now we have an equation where gamma is constant due to our assumptions of perfect gas, chaotically perfect gas, and three varying quantities, PO2, P1, and M1. Unfortunately, you can see we cannot exactly make a closed form solution for M1 easily. Let's try an example, and you'll see that we have to solve the equation numerically. We have to try and find the flow Mach number using a pitot-static tube. The device measures static pressure as 20 kPa at the device, and a total pressure as 32 kPa. A second measurement is performed, and the static pressure is 20 kPa, and the total pressure is 80 kPa, measured by the probe. Assume that gamma is 1.4, Cp over Cv, that is. Now we look to find the Mach number for both particular measurements. Let's try that out. First, we'll see if the flow is supersonic or subsonic. Let's examine the critical pressure ratios. Recall, as we discussed previously, the critical pressure ratio, that is where we deaccelerate the flow or accelerate it to Mach 1, must be greater than a particular pressure ratio. In nozzles, the nozzle pressure ratio. So we'll write P naught over P critical goes as gamma plus 1 over 2 to the gamma over gamma minus 1, which is the critical pressure ratio. And that goes as 1.89293 for, of course, diatomic gas gamma 1.4. So the first case in the example, the first probe, it's the same probe in both examples, will have a ratio of P naught over P, 32 over 20, kPa is 1.6. 1.6 is indeed less than 1.89. That means the flow is subsonic. So for the subsonic flow case, I am not even interested in analyzing this particular problem in the example, because we've done this problem earlier for the traditional compressible pitot-static probe case. So we won't review the solution because it's the same approach as previously done, and we would just use isentropic theory for Mach number with the total pressure to the static pressure relation to solve the problem. We can then, remember, do not use the incompressible Bernoulli equation in either of these cases because, of course, the speed of the flow and Mach number is high, and we would neglect and find error. Now let's check the Mach number for the second measurement using the critical pressure ratio. You see that the probe measures a total pressure of 80 kPa and a static pressure of 4. The ratio of 80 to 20 kPa is 4. Therefore, 4 is greater than 1.89, which is the critical pressure ratio, and therefore the flow is indeed supersonic. Now, unfortunately, we'll require an iterative method to solve the Rayleigh-Pitot equation, or maybe fortunately if you love numerical methods, to find the solution. Well, guess what? You learned actually how to solve this particular problem exactly in your numerical methods classes in math or perhaps in our own department. We'll try and rewrite the so-called Rayleigh-Pitot formula, which I have written in equation 445 of the slide deck, as a function of Mach number, which goes as am 2 to the gamma minus bm squared plus c equals 0. You can then take A, B, and C and plug in the coefficients found in 445. You can try and do that yourself. If you do that hard work, you can find that A equals gamma plus 1 to the gamma plus 1 all over 2 gamma minus 1. B equals 4 gamma times PO2 over P1, a familiar term, to the gamma minus 1. And C equals 2 times gamma minus 1 of PO2 over P1 to the gamma minus 1. Lovely. Let's try and continue and find the particular solution. Now we'll take the derivative of 447 and we'll find that the dm, the derivative of f, which is the right-hand side of 447, with respect to Mach number is 2 gamma times am 2 gamma minus 1 times 2bm, which you can see in 448 through differentiation. Simple. Calculus 1, right? Now, we can use the famous NewtonRaphson method to find the particular solution, and this is written as an iterative approach. If you don't remember this, it's time to get out your numerical methods textbooks and review. So, you'll have the new Mach number will go as the old Mach number minus f of m old divided by df dm of m old, and we'll have to guess an initial Mach number m with a realistic value. We can then insert f of m old divided by the derivative of f of m old on the right-hand side, and we'll get, indeed, 2 gamma minus 1 am old squared gamma minus bm old squared minus c all over 2 gamma am old 2 gamma minus 1 minus bm old times 2. So indeed, for these particular values, for gamma 1.4, A, B, and C, with the pressure values will be 6.19, 5766, B, 9.750166, and C, 1.3928881. You can indeed iterate your first guess as M2. You can guess any realistic value, 1.5, 2, 5, 3. However, Mach number of, say, -5 or 0 or 0.1 may not be a good guess, and it would not guarantee convergence of the numerical method. I always try and suggest putting in a Mach number of a realistic value. Let's try and solve this problem iteratively now. Remember, iterative methods require a guess, and we'll do 5 iterations and check our convergence using Newton-Raphson algorithm. So you can see this particular table. On the left column, we have our iteration n from 1 to 5. We have our Mach number, which for a first guess of 2. And then from that Mach number, the third column will be a function of m, which is, of course, equation 447. And we can evaluate the derivative df of dm, which will be 21.4, which is in 449. And we can calculate m nu, which of course is left-hand side of 450. From m nu, we would then calculate the second iteration, and calculate once again FM, DFM, and another M new at n equals 2. We repeat this process, which is why it's called iteration, until we find a particular value at iteration 4, 1.64748. We then find FM and DFM, and we find M new being 1.64736. And I should have put 1.64736 right here. I apologize for that. But you'll see, once again, after the 5th iteration, our value doesn't change. And so M new minus M old, the magnitude becomes very, very small, and that would be an L1 norm of convergence check, which we can say the method is converged. You should try this on your own for different values of guess M over a number of iterations and see how your convergence progresses. Indeed, there are tables of the Rayleigh-Pitot equation relating Mach number and pressure ratio. For example, for every pressure ratio, we've tabulated M in the Rayleigh-Pitot equation. So this has been done for you by computers by looping over a series of Mach numbers and or total pressure to static pressure ratios. Indeed, that's what's done numerically in the JavaScript code in the Rayleigh-Pitot formula. At the top of the page, we've written one form of the Rayleigh-Pitot formula. That's the total pressure, PT, written with T for total, at the probe, divided by the static pressure in front of the shock, goes as a function of Mach number and gamma. If you go to the compressible flow calculator or go to the website, you can indeed see the normal shock relations. In the normal shock relations, which we've talked about before, you can put in a value of gamma, a Mach number M1, and let's say it's 2, that's the Mach number in front of the probe in this case, or the Mach number M1 in the Rayleigh-Pitot formula, and hit calculate. You'll see there's one box here. This little box will appear, and it's P1 divided by PO2. Indeed, that's the inverse of PT over P1 in the Rayleigh-Pitot formula. So if you know the static pressure, and indeed you know the total pressure from the probe measurement, you can find the Mach number measured by the probe at that particular location as if the probe wasn't there. Here's one particular Schlern of another Pitot probe here. This is a U.S. Army photo from the Ordnance Aerophysics Lab in the 1950s. It's a Schlern image. Here's the probe body. The fluid moves left to right, and you can see there's a normal shock forming in front of the probe. Indeed, you can also use tables, which are summarized in the tables of your class. In the class handout. And these tables do, of course, have a column M1 across the left-hand sides and center right-hand columns. And they have a corresponding Rayleigh-Pitot column. And we'll look at these tables and discuss them together in our one-on-one sessions and Q&A or recitations. You can easily use the table to look up the values of the Rayleigh-Pitot formula. And so that way you don't have to do a numerical method. But I encourage you to try and program your own numerical methods you can learn. In this class, we covered 3 major subjects. 1, the induced velocity behind the shocks and the induced Mach number, which can indeed be supersonic. We then looked at reflected shock wave cases and talked about solving reflected shock problems and their ideal Mach numbers that can be induced. We also remember to look at the boundary conditions so we can enforce the continuity condition. We then looked at the Rayleigh-Pitot probe formula and gave one particular example. And note we have to solve it with numerical methods. And the numerical solutions are summarized in, of course, our tables. Computers, of course, discrete computers do this automatically through different types of numerical methods to solve the equation. Thank you very much for your time today. I'm Professor Steve Miller.